Hey everyone, welcome back. We're learning about semiconductors. In the previous lesson, we learned about one type of four-terminal semiconductor device. Can you recollect what we saw? Yeah, we saw about photocouplers or optocouplers. In this lesson, I'm going to walk you through another type of a four-terminal device called as the Hall effect sensor. What does a Hall effect sensor mean? Let's break down the concept. So these are devices that are used to measure the magnitude of the magnetic field. That is, we could measure the intensity of the magnetic field. Take a look at this diagram. This is how a Hall effect sensor is represented in circuits. Note that they have four terminals through which current can either flow in or flow out of the device. Now the output voltage that is produced by this device is directly proportional to the magnetic field strength applied on it. If the Hall effect sensor is subjected to high magnetic field strength, then the output voltage is also high. If the magnetic field strength is very low, then the output voltage is also considerably low. Where are these Hall effect sensors being used? They are used in proximity sensing, in positioning, speed detections in cars and automobiles, and also in current sensing applications. Now let's see, what does Hall effect mean? Consider that we have a semiconductor device in which we apply a voltage and so we have current flow through it. The electrons move in this direction. Now what happens when I subject this semiconductor device to a magnetic field? We have magnetic flux density B being produced. Now due to this magnetic flux density B, we have our holes and electrons being accumulated or deflected towards the edges of the semiconductor device, and thus the current no more flows in a straight direction. Instead, the current deflects towards the edges of the semiconductor device and then flow. Now in this case, we could also use a conductor instead of a semiconductor. However, in semiconductor by default we have our holes and electrons, and thus the output voltage or the potential difference that's being created is significantly high when we use a semiconductor. Now, when I use an external device such as an ammeter to find if there is current flow, we can find that there is a potential difference that's being created between the edges of the same device, and thus we have more current flow. In case I had just holes or electrons, then there is no potential difference and the reading would be zero. So as we saw above, even conductors could be used, but we use semiconductors since by default they have holes in them. Now we have two types of Hall effect. One is the analog signal and the other is the digital signal. Now this classification is based on the output that's being produced by Hall effect sensors. So analog signal looks something like this, and a digital signal looks something like this. Now moving on, let's see how are these Hall effect sensors being formed. Now, the construction involves a p-type semiconductor. Can you recollect what p-type semiconductor is? Now, p-type semiconductor is made up of a combination of a trivalent impurity atom with an intrinsic semiconductor material, such as gallium arsenide, indium arsenide. And so, when we combine the p-type semiconductor material and pass continuous current through it and subject it to magnetic field, we have what is called as the Hall effect being produced in them. So the movement of these electrons is affected by the external magnetic field. And you also have to note that the magnetic field is subjected only at right angles to these devices. So this process of generating voltage using magnetic field is what is called as the Hall effect. Now that we know about what is Hall effect, let's see how it affects or doesn't affect what we see in our daily life. So Hall effect sensors are affected by magnetic field. This is what we've seen up till now. Now have anyone got a doubt that Then what happens to all the magnetic fields that we see in our daily life, such as compass and earphones? Are all these devices also affected by Hall effect? No. So, what happens if I walk with a large magnet in a radio station? Will the radio station be also affected by this Hall effect? That doesn't happen. This is because when I increase the distance, the magnetic field strength is being reduced. Approximately, I could put it in simple terms that when I double the distance, it quarters the magnetic field strength. And Hall effect is produced only for very, very close proximity and for high magnetic field intensities. Then what happens to Earth's magnetic field? Is that affected and produce any Hall effect on us? No, it doesn't affect because the distance is more and the strength is also less. Now, Hall effect sensors are usually designed for high magnetic field intensities. Then what happens to devices such as compass, earphones and flight controllers that have magnetic field in them? These devices are designed in such a way that they respond only to very weak magnetic field. Moving on, let's see the types of Hall effect sensors. There are two types. One is the unipolar and the other is the bipolar. By the name, it's very evident that unipolar has something to do with single direction or something single, and bipolar has something to do with bi or two things. Now, unipolar Hall effect sensor means that these sensors require just one magnetic south pole, that is a positive south pole, to operate and both release as they move in and out of the magnetic field. But in bipolar, we require a magnetic field that has a positive south pole to operate, and we also require the north pole having a negative field to release them. And so finally we've come to the end of this lesson. Let's have a quick recap of what we saw in this video. We saw about what is a Hall effect sensor, which is a four-terminal device through which current can either flow in or flow out of the device. We saw that Hall effect sensors are used for proximity sensing, positioning, speed detection, and current sensing applications. We also saw what is Hall effect. That is, a potential difference is being created when a semiconductor device is subjected to magnetic field because we have something called as the magnetic flux density B that's being generated, causing the holes and the electrons to get deflected and accumulated at the edges of the semiconductor device. We also saw that we could use a conductor instead of a semiconductor, but semiconductors have holes and electrons, and so we prefer a semiconductor device to be used in a Hall effect sensor. We saw that there are two types of Hall effect, analog signal and a digital signal. We also saw about construction of a Hall effect sensor, which uses a p-type semiconductor such as gallium arsenide, indium arsenide. And finally, we also saw that these devices are specifically designed to respond to high magnetic field intensity and is not affected by Earth's magnetic field or any other device that uses weak magnetic fields such as earphones, compass, and flight controllers. And finally, we saw that there are two types of Hall effect sensor, unipolar and bipolar device. Well, thank you for watching, and in the next lesson we will be learning about the applications of semiconductor device, which will be the last lesson of this course. Stay tuned for more.